Bismillahirrahmanirrahim. Today I will start with resonators. And as you know, resonators occurs whenever a system has complex conjugate poles, or in a circuit, if we have RLC circuit, then we can have a resonance in there. And the resonance, we have two types of resonance circuit. One is the series resonance, and the other one is the parallel resonance. So these are resonators. One is series resonance, and as I said, we have to have at least one inductor and one capacitor in the circuit. Otherwise, there will be no resonance. So let's say this is VI R J omega L 1 over J omega C. So this circuit, at certain frequency, it will resonate. So if we find Z here, then Z simply equal to R plus J omega L plus 1 over J omega C. The concept here is that at one frequency, that's called the resonance frequency, this inductor, reactance of this equal to this, and they are opposite in sign, because as you can see here, this can be written as R plus J omega L minus J over omega C. So you can see this term can be set to 0 at one frequency. So we can rewrite this as Z equal to R plus J omega L minus 1 over omega C. So we have to set this equal to 0, and hence our impedance will be pure resistive, meaning these two will be shorted out, and hence we'll have a maximum current. If we are shorting these two, because this equal to this, but they are opposite in sign at one frequency, then we call that frequency equal to resonance. So we have to set this part equal to 0, and that will give me the frequency, resonance frequency. So if we say this part, so we have omega L minus 1 over omega C should equal to 0, or omega L equal to 1 over omega C. If we cross omega times C, if we multiply, then omega square equal to 1 over LC, and we can say the resonance frequency omega R is equal to 1 over square root of LC. If it is series resonance or parallel resonance, then this would be the resonance frequency, because we said that if you have at least, you should have at least one capacitor, one inductor in a circuit to have a resonance. Otherwise, it will not resonate. So that's the first step. So we have to know what is the resonance frequency, and this is the way to write it. So what we have done, as you can see here, we have to set any imaginary part in Z or Y. Or in parallel resonance, we can find Y. In Z or Y, we have to set the imaginary part equal to 0, meaning the phase shift of Z, or the angle of Z, is 0, or V and I will have the same phase. So that is the concept here. At resonance, the angle of Z or Y should be 0, or the volt and current should be in phase. That's number 2. The third, the current is maximum, meaning this will cancel each other, and we have maximum current in this. So that's the first thing. So the first thing we have to find is omega R, all right, which is the resonance frequency. Now, other terms we have to find. So if we sketch the frequency response, let's say for Z now, Z, then we have something like this, right? Okay. So that is, this here will be your center frequency, okay? So usually we can express this in terms of volt, which is I times R. Then we can say this is volt here, the magnitude of the volt, and this is the maximum. So this will be V max. Now, other terms we have to know are the minus 3 dB, which is 1 over root 2 times V, right? That is this point. So we have here now 2 points. The first one we call it omega C1. This is omega resonance. And the second one is omega C2, right? The difference between these two is called the bandwidth. So bandwidth will be omega C2 minus omega C1, right? So these are the important terms we have to worry about in any resonance circuit. We have to know what should be the resonance frequency. We can derive it, as I said. The second thing is what will be the half power omega, which is, we call this half power, or minus 3 dB, or whatever we have, or cutoff frequencies. Then we have omega C1 and omega C2. Then we have the bandwidth, which is the difference between the two, right? That's the bandwidth. And then we have what we call the quality factor. Because if the response can be like this, can be sharp. Now this depends on the quality factor. If Q is high, greater than 10, it will be sharp. If Q is less, it will be wide. So that is how we distinguish between them. So we can say we have high Q or low Q. Okay, so sharp or wide. Now, as you can see from the response here, we have if we call Z, this means this is volt over current. Huh? So that is your Z, volt over current here. Okay. If we just draw Z, that is volt over current. Now to find, if we think about it as symmetrical response, then we can find omega C1 and omega, we can find the bandwidth, right, is equal to omega C2 minus omega C1. So that is the bandwidth, okay, which is the difference between these two. So bandwidth will be taken from the cutoff here, which is the half power. We call it the half power, all right, or the cutoff frequencies. And then we have to find the quality factor, Q. Q for this actually, or we can say the bandwidth, right, is also can be written as omega R over Q. As you can see now, this is explaining this curve. If we increase Q, we will reduce the bandwidth, so we'll make it sharper. And then we can find, we know that the bandwidth will be omega C2 minus omega C1. If it is sharp, then we can simply find omega C2 and omega C1 from omega R. So we can say that this is the center frequency. So if it is symmetrical, this is half of the bandwidth, this will be half of the bandwidth, then we can say omega C1 is equal to omega R minus half of the bandwidth, and omega C2 is equal to omega R plus half of the bandwidth. So this is the easiest way to find. So if we assume symmetrical response or high Q. How high is high? Q is greater than 10. So if Q is greater than 10, we can say this is a high Q. And in this case, we can use simply these equations to find omega C1 and omega C2. If this is not the case, right, then we have to go to the half power equation, right? So we have to set Z max to the half power of Z max. Then we have to find omega C1 and omega C2, and this can be written as omega C1, omega C2 is equal to plus or minus alpha square root of alpha square plus omega n square or omega r square, where alpha is equal to r over 12. So this is the other way to find omega C1 and omega C2. So omega C1 will be with the minus, so we have this also plus. Okay. So you have omega C1 will be the minus sign, omega C2 will be the plus sign. So this is the other way to find it. Like in resonance, usually we assume that it is symmetrical, the response is symmetrical, so we can use these equations to find omega C1 and omega C2. طبعا quality factor Q, which is we can find Q in terms of the components. So we can say that by definition, Q equal to 2 by maximum bar absorbed, stored in L in this case, divided by power dissipated in the resistor, in one period, in one period. Okay, so in this case we can say Q equal to 2 pi, and the power stored in the inductor is I square, right? Half L I square, that is the peak value here, IL square, which is I actually, divided by the power dissipated. The maximum here will be half I square R, right? I square R into one period, which is T. We can say it is 1 over F. So as you can see, this will cancel this will cancel this, and we are left with 2 by F L over R. So you can see that Q is equal to 2 by F is omega. So that is omega R times, because we are evaluating this at resonance, omega R times L over R. So this is the quality factor. So you can find it from here. Q is equal to omega R into L over L, L over R. Now this here, we can also relate it to the bandwidth also, because we have the bandwidth relation with Q. So this is for the series resonance. Now we can have a parallel resonance. The second one. Parallel resonance. So in this case we have R, L, C. And we can use current source, let's say, here, and we can find V here, or we can find Y, right? So this is R, J omega L, 1 over J omega C. So you can say Y equal to 1 over R plus 1 over J omega L plus J omega C, right? So this is equal to 1 over R minus J over omega L plus J omega C. This can be written as 1 over R plus J omega C minus 1 over omega L. So this part should be set to 0 so that we have a pure resistive impedance. And we have, for this to be true, omega C equal to, 1 over omega L, or omega I square equal to 1 over CL, and hence omega R is equal to 1 over square root of LC. So you can see that the resonance frequency for parallel or series resonance is the same, 1 over LC. And similarly, we can find Q, right, equal to omega naught over beta, and beta equal to omega C 2 minus omega C1. Again, omega C2 and omega C1 are the half power frequency. Here we can rewrite this in terms of the bandwidth, because the bandwidth is 1 over RC, so this will be omega naught over RC. Omega naught times RC, omega naught times RC, so the omega resonance times RC. So this is also the same, and you can find it also in terms of L. So it will be omega R over omega naught L, R over omega naught L. So this is the same thing. That's for Q. Right. Let's take a simple example here. And just we'll apply what we learned in this. Assume that in a series resonance, RLC resonance circuit, we have RLC where we have R equal to 2 ohms, L equal to 1 millihenry, and C equal to 0.4 microfarad. The question is find omega resonance or omega node, omega C1, omega C2, Q bandwidth. Right? Sometimes they call it P only, yeah? So in some texts it is bandwidth, in sometimes it is I max and I of WC1, let's say. So that is the symmetry. Right? So we can say first one omega naught, we know it is 1 over square root of LC, just we have to substitute the value. So this is 1 over L, which is 1 times 10 to minus 3 into 1 into 0.4 times 10 to minus 6, and this will give me 50k radians per second. So that's omega, not F. So to find F naught, we can say A equal to omega naught over 2 pi. So you have to divide by 2 pi. That's the first one. Second one, find omega C and omega C1 and omega C2. So we know that Q equal to omega naught times L over R. So this is equal to 50k times L, which is 1 milli, divided by R, which is 2. So the K will drop the milli. 50 divided by 2, that is equal to 25. Now if we know Q, we know omega naught, we can find the bandwidth. If we know the bandwidth, then we can find omega C1 and omega C2. So we can say, okay, now the bandwidth is equal to omega naught over Q. So this is 50k divided by 25, so that will give me 2k. That is the bandwidth 2k radians, radians per second. That is the bandwidth. Now to find, if we know the bandwidth, then we can say that omega C1 equal to omega naught plus half, minus half of the bandwidth. So it is equal to omega naught, which is 50, minus half times 2k, that is k. So this will give me 1, so that is 49k. So that's omega C1. And omega C2 is omega naught plus half of the bandwidth. So it is 50k plus 1, that will give me 51k radians per second. So this up to here, Q and bandwidth, we know it now. Then Imax, since this will be shorted out, so Imax will be V. V is given as 20 sine omega t. This is 20 sine omega t. So the maximum will be 20 divided by R. So you can say Imax at resonance, which is at omega naught, is equal to 20 over 2, and that will give me 10 ampere. I at 3 dB, well, half power, or at omega C1, which is the same as omega C2, is 0.707 or 1 over root 2 of Imax. So that will give me 0.707, right? Times 10, so that will be 7.1 almost, so 7.1 amps. So that is the the current here, the maximum current is here, and current is here, okay? Right. Now let's take another problem where we have another type of resonance circuit. As I said, resonance will occur only if we have a circuit that contains L, at least one inductor and one capacitor, right? So let us assume we have the following circuit: capacitor, resistor, then we have inductor in series with the resistor. So that's the change here. So we have, this is 10 ohms, 0.1 farad. That's the current here, I don't care about what's different there. This is 2 Henry, and this is 2 ohms. So the question is, find omega naught, the resonance frequency, okay? Find omega naught, which is the resonance frequency. Now we cannot simply say that omega naught is 1 over LC, because this is not a parallel, not a series, because we have these 2 ohms resistor here. So in this case, we have to find Y here, right? So you have to find Y. You can find Z if you like, but since they are in parallel, you can find Y. So we can say Y is equal to J omega C plus 1 over R. Let's say C, L, let's call this R1, and this is R2, okay? Or we can simply substitute. So plus 1 over R1 plus 1 over 2 plus J omega L. Alright, so this is the admittance. Okay, this is the admittance here. So in this we have now to find a way to express to make the imaginary part equal to 0. So this can be written as J omega C plus. Now this, what you can do, we want to remove one of the terms down, so we can multiply by the conjugate of this. So we can say this is 1 over 2 plus J omega L into 1 minus J omega L over 1 plus J omega L. And you can substitute value in this case. Okay, you can substitute value in this case. So this is omega naught. Okay, we'll call it omega naught because we want to solve for omega naught. Okay. This is 1 over R, so we should not worry about it much. And this one is J omega C, so that is J omega naught C plus, now this becomes now 1 minus J omega L, that is up, and down we'll have, this is 2, sorry. This is 2. And this will become now 4, because this will be magnitude, plus omega square L square. Okay? Omega naught square. Okay? So now we can rearrange this. So we say Y equal to 1 over R plus this term, 2 over this term is a real number. So we can say 2 over 4 plus omega naught square L square minus J omega L divided by 4 plus omega naught square L square. Okay? Plus J omega C. J omega naught C. I don't care about this. I have to care about this. So we have to set this equal to 0. This should be equal to 0. Because this is a real part, so we want Y to be only a real part. So we have to set this to 0, and from this we can find the resonance frequency. So we can say J omega naught C is equal to J omega L. طبعا الجي حيطير مع الجي, we don't care about it. So we have omega L divided by 4 plus omega naught square L square. So if we cross multiply, this actually will cancel this. So we have 4C plus omega naught square L square is equal to L, right? Or omega naught square is equal, L square is equal to L minus 4C. Or omega naught square is equal to L minus 4C over L square. So omega naught will be square root of L minus 4C over L squared. So that will give you the resonance frequency. Okay? So now if we substitute values, then we can just plug numbers here. So this will be L square root of L is 2 minus 4 times 0.1, that is 0.4, divided by L squared, that is 4. So that will give me the resonance frequency here. Okay? That will give me the resonance frequency. Okay. Right. Yeah, so you can just substitute and get the value of omega naught. So omega naught will be in this case, let me see, what is it? Okay. Anyway, this is the solution for it. Another problem that is from your notes, handout, sorry, from the handout. Let's assume we have the following circuit. Okay. And we'd like to find J omega L, 1 over J omega C, and we want to find the resonance frequency for this. Okay? Find an expression. For omega naught, which is the resonance frequency. Okay? Right, so we can say y equal to this in parallel and series with this, right? So we can have this, or we can find z here. So you can say z is equal to j omega L in parallel with r plus 1 over j omega c. So that this can be written as j omega L multiplied by r 1 over j omega c divided by j omega L plus r plus 1 over j omega c. Just we manipulate this equation, so we can say j omega L into j omega c, then we have j omega c r plus 1 divided by, we can also say, we take j omega c common here, so this will be j squared omega squared L c plus j omega c r plus 1. Now this will drop this. These two terms will drop each other. And we can rearrange this, so up we'll have, that's the j squared, so that will be minus omega squared LCR plus j omega L. Okay? J omega, j squared omega squared LCR plus j omega L. And down, denominator, we have, this will be 1 minus omega squared LC plus j omega CR. Now here, as you can see, we have j up, j down, and we must set the face of this equal to 0. So we cannot set this imaginary equal to 0 because there is no negative part here. We cannot set this imaginary equal to 0 because again there is no negative j here. So we have to work it in two ways. Either we have to multiply by the conjugate of one of them, either conjugate of this or conjugate of that, or we have to find theta here, theta there, and make them equal. So if you make them equal, then theta of z will be 0. يعني if theta of this will be tan inverse omega L over omega L square LCR divided by theta of this will be tan inverse omega CR over this. Now equate these two terms and you will get the resonance frequency. The other way is, so you can say one way, yeah? Case number 1. So we can say tan theta اللي هي ايش؟ tan inverse of omega L, right? Over minus omega square LCR should equal to tan inverse omega CR divided by 1 minus omega square LC. Okay? Or, so we can remove tan, then we have omega L over omega square LCR should equal to omega CR divided by 1 minus omega square LC. So you can, this L will drop this L, this will drop that, and we have this is minus L. So we have minus omega naught square C square R square equal to 1 minus omega naught square LC. So if we take this to the other side, then we have minus omega naught square plus C square R square plus omega naught square LC is equal to 1. So if we take omega naught square عامل مشترك, so we have here LC minus C square R square equal to 1. Or omega naught square is equal to 1 over LC minus C square R square, and hence omega naught is equal to 1 over square root of LC minus C square R square. So this is one way. Instead of having the multiplying by the conjugate, then you may get some mistake. Just you have to set theta equal to 0 for z, right? And you can get the resonance frequency omega naught, right? Right. So that is regarding resonance. Now in filters, or before, filters or transfer functions, let's say, we have 4 types of filters. And we'll talk only about low pass, high pass, and band pass. And band reject, so filters. And these filters are, we call them passive filters because we are using only RLCs. Okay. So low pass filter, we have high pass filter, and band pass, and band reject. So these are the 4 common types of filters, band reject filter. Now we can implement the filter using low pass filter. Let's say low pass filter, and we'll stick to the first order. So we can implement the low pass filter using LR or we can use RC, so RC. Okay. So this is your input. So this is VI, should be sine signal or whatever, as you can see, and this is your V up there. Same thing here. This is VI, RC, and that's V out. Okay. So this is a low pass, and this also low pass. But this one we are using RC, and this one we are using RL. So if we call this J omega L, right? And that is R, and we can find the relation between them. So V out using the voltage divider is VI times R over R plus J omega L, or we can say VO of S. So as a function of S in S domain is equal to VI of S times R over R plus SL. Okay? This is in S domain representation. So you can see J omega is S. Like let's take to the J omega, and we can say V out or H of S, H of J omega manifold is equal to V out of J omega over Vi of J omega, and that is equal to R over R plus J omega. Now here we have to make this in the standard form R over R plus SL. To find the cutoff frequency, then we have to make the coefficient of S equal to 1. So you can say H of S now is equal to R over خدنا L عامل مشترك. So L عامل مشترك. This will be S plus R over L, and this can be written as R over L divided by S plus R over L. So this is in the form of K or omega naught over S plus omega naught, where omega naught is our cutoff frequency. So the cutoff frequency of the filter, if this is the frequency response, right, that is omega, that is gain, AB. Then for low pass filter, this is the response, and the 3 dB frequency is this. So we call it F node, or the cutoff frequency, or 3 dB frequency. So in this case, F node is R over L. So if we know R and we know L, then we can tell what is the cutoff frequency of this filter. Now, the complete response is to find the magnitude response and the phase shift response using this equation. So you can find the magnitude from here. This is R divided by square root of R squared plus omega L squared. That is the magnitude, and theta will be minus tan inverse omega L over R. That is the phase shift. And then you can sketch as you vary the frequency. So this is the low pass filter. So as I said, you have to put it in the standard form. S plus, you make the coefficient of S all the time equal to unity. Similarly, we can do this here. We can say V out is equal to Vi into 1 over SC divided by R plus 1 over SC. So H of S is equal to 1 over SC over, we can take SC common factor here, so this will be 1 plus SCR, this will cancel this, and we have 1 over 1 plus SCR. Again, this is not standard form, so we have to make coefficient of S equal to 1, then we say H of S is equal to 1 divided by CR is a common factor, S plus 1 over CR. Then this can be written as 1 over CR over S plus 1 over CR. And this is the same. It is omega naught over S plus omega naught. So in this case, omega naught is 1 over CR. So this omega naught is 1 over CR. And this one, omega naught is R over L, right? And in this one, that is A magnitude, okay? Omega 3 dB That is F naught is equal to 1 over RC OCR. So this for the low pass filter. Okay. Now depends on what is your requirement. You can design your filter to satisfy your requirement. For high pass, one note here, we don't prefer to use inductors because they are bulky, volumes large, difficult to find different numbers or different values, right? So we prefer to use the RC, okay? But we call these filters passive filters because, as you can see, no active element is involved in the design of this. But we have active filters. You'll study this in 303, where we have to use op-amps in the circuit, okay? Now, the things in the bad thing or the disadvantages of these filters, the maximum gain you can get here is 1, so you cannot have more than unity. So there is no gain actually. The maximum is unity. Okay, that is one drawback. And let us assume I want a filter at the same time I want to amplify the signal. Then we cannot use passive filter for this. Luckily, they have good things. That the frequency range is very large, so you can go mega, giga. There is no problem. However, when you use active filters, there is a limitation. Okay, so we cannot just go in any range of frequencies. We are restricted by the integrated circuit frequency response of amps in fact. Right. For high pass filters, we do it the other way around. Okay, so this is VI R L, and we have here V out. So you can see now V out is equal to VI into j omega L over R plus j omega L, or we can say H of S is equal to S over R plus SL. So we can rearrange this, take L common factor. So we have S divided by L S plus R over L. So this will give me LS over S plus R over L. This is your omega naught, okay? And that will be your K here. So you can, the form is for high pass filter, H of S is KS over S plus omega naught. So that is the general form of the high pass filter. If we use RC, then we have just to exchange the places here of R and C, and we'll do the same thing. So we can say V out is equal to VI R over R plus 1 over j omega C. So H of S is equal to R over R plus 1 over SC. So this can be written as SCR over over 1 plus SCR. أخذنا عامل مشترك SC هيطلع فوق. Then we have to rearrange this. So we say H of S is equal to SCR over CR عامل مشترك. Here we have S plus 1 over CR. This will drop this, and we have S over S plus 1 over CR. So this is the standard form for the low pass. So it is S over S plus omega naught. Okay? Why you have this here? So we have SL here. Oh, sorry. This is SL. So this is L, but this will cancel, huh? That's why. This will cancel. So this is cancelled here. So it is S over S plus omega naught. So this is for the low pass filter, the high pass filter, sorry. So what you have to find in the low pass filter, you have to derive the transfer function. You can also identify the type of the filter by inspection here. So let's just look at these two here. So let's say I don't know if this is a low pass or high pass, and you are asked to find by inspection what is the type of the filters here. First, we know it is a first order because we have only one reactive element, so it is first order filter. Now, is it high pass or low pass? We have to see. We'll say at low frequency, this will act as open circuit, so that there is no current, the output will be zero, so this must be high pass filter, because at high frequency it will become short and V out equal to Vi. On the other hand here, at low frequency, this is open circuit, so V out will be the same as Vi. At high frequency, this will be shorted down, so it will become zero, and V out will be zero, so we know that this is a low pass filter. Similarly for this one, at low frequency, this is short circuit, so it is zero. At high frequency, this is open circuit, V out equal to Vi. So by inspection, you can tell if the filter is low pass or high pass, or if in band pass or band reject. You can do that by inspection, and you can get it using using the transfer functions here, right? So this high pass, because you can look at this in a different way. So you can take S common factor, right? And then you can see when you sweep the frequency, high frequency, what will happen to your transfer function. All right. Now let's go to the complex frequency issue. Well, before that, let's see the band pass filter, right? The band pass filter. Yeah, we have RCL, so that is band pass filter. Band pass filter. We have L, R, and C. That's going to be V out, Vi. So this is the omega L or SL, you can say. R 1 over SC. So we can say V out is equal to Vi into 1 over SC over R plus SL plus 1 over SC. So H of S is equal to V out over Vi is equal to 1 over SC divided by R plus SL plus 1 over SC. If we take common factor of SC here, so this will become SCR plus S square LC plus 1. And this is 1 over SC. So this we cancel this. And we have H of S is equal to 1 over S square LC plus SCR plus 1. The standard form, we have to make S square coefficient equal to unity. So it means we have to take LC as a common factor. So you can say H of S is equal to 1 divided by LC. There you have S square plus SCR over LC plus 1 over LC. So this is the standard form. So H of S is equal to 1 over LC divided by S square plus C will cancel C. S R over L plus 1 over LC. Now this term is omega naught square. This term is the bandwidth, right? Which is Q over omega naught. Omega naught over Q. Okay. And this one is omega naught square. So we can write it as H of S is equal to omega naught square divided by S square plus S omega naught over Q plus omega naught square, where omega naught equal to square equal to 1 over LC, and hence omega naught is equal to square root of 1 over LC. So that is, this is the center frequency here, right? LC. And now this is your bandwidth, okay? Bandwidth which is R over L. And if we sketch this, we'll have the same thing as a resonance circuit. But what you can see now here, band pass filter is a second order filter. We cannot say there is a band pass filter which is first order, because we must have at least two reactive elements, and this reactive element will give me the S square. So the band pass filter should be second order by default. Okay. Now depends now on Q. Omega naught over Q is the bandwidth. So if we increase Q more than 10, we can say this filter is narrow band. If Q is less than 10, we can say it is wide band filter. So this is for the band pass filter. And we are left with the band reject filter. So the band reject filter band stop or band reject. Band reject. So in this, we will have the capacitor and inductor are in series. So we have inductor, capacitor in series, and we can have two versions of this. So we can take V out from here, that is R, SL, 1 over SC, and that is my input, VI. So you can say V out is equal to VI into SL plus 1 over SC divided by R plus SL plus 1 over SC. So H of S is equal to, here we have SL, S square, LC plus 1 over SC, خدت عامل مشترك SC, divided by SCR plus S square LC plus 1 over SC. So this will cancel that, and we are left with 1 plus, well, I can take LC عامل مشترك, so LC عامل مشترك, we have S square plus 1 over LC divided by, here we take LC عامل مشترك, so we have LC out, we have S square plus SCR over LC plus 1 over LC. So this C will go with that C, LC will go with LC, and our transfer function is H of S is equal to S square plus omega naught square divided by S square plus S omega naught over Q plus omega naught square. So at a frequency equal to omega naught, the H of S will become 0. So you can see that this is the band pass response. Okay, that is A. So this is band pass. And this will be a band reject. Okay, so this band reject response as a function of omega. So this at a frequency omega naught, this becomes 0. So you are eliminating or rejecting a certain noise. Like the 60 Hz I want to eliminate, then you can use the band reject. If I want to pass band of frequencies like the FM 106.1 or 90 megahertz, then I can tune my filter or design my filter so that this is 90 megahertz, and I can make it sharp so that I cannot hear any other frequencies coming from other stations. So this is basically the 4 common type of filters we have to know about. Then we have some details, like what will be the half power. So this is the minus 3 dB here frequency. Same thing here, what will be the half power frequency here. Okay, so we have to find these values and the bandwidth, and we know that the bandwidth equal to omega naught over Q, right? Bandwidth equal to omega naught over Q. Now with this term you can find the other parameters. parameters, and we know that the bandwidth, which is R over L in this case, right? Which is omega over Q. You can design your filter so that it meets certain specifications you have in your mind. This is about filters. Now let's just turn to complex frequency. So we'll take one example on complex frequency just to show you what's going on. Let's assume that